Hi, everyone. I'm Chris Gearhart, the Director of the Center for Integrated Mobility Sciences at the National Renewable Energy Laboratory. I'm here today to talk about the role of simulation in sustainability research. I want to thank the conference organizers for giving me the opportunity to speak to you about sustainability. But before I get started, let me take a few minutes to make sure everyone is familiar with NREL. NREL started as the Solar Energy Research Institute in 1977 due to concerns over the 1973 oil embargo. In 1991, we were elevated to the status of national laboratory and changed our name to the National Renewable Energy Laboratory, NREL. Today, NREL employs about 2,600 people. At NREL, we focus on creative answers to today's energy challenges. Our research ranges from breakthroughs in fundamental science of renewable power, sustainable transportation, and energy efficiency, and the knowledge needed to integrate that science into optimized energy systems. NREL is the only national laboratory solely dedicated to advancing renewable energy and energy efficiency. Our commitment to scientific discovery helps to fill the gaps in energy knowledge and to develop next-generation energy technologies. The laboratory responds to market challenges by identifying these knowledge gaps and providing market insights that inform the technology landscape. This market-facing approach positions NREL to have impact across a breadth of industry sectors while simultaneously growing the nation's body of energy research. Today, I want to talk about the role of simulation in sustainability research, but I need to add a caveat to that. I'm a transportation researcher, so I'm going to talk mostly about making transportation sustainable. So let's talk about sustainability as it applies to the transportation sector. Let's look at the numbers. The demand for transportation in the United States is high, and it's growing. Thinking just of the on-highway transportation system in the United States, drivers travel more than 3.2 trillion miles per year, and business transports nearly $12 billion in freight. The typical American spends more than $9,000 a year on transportation. Vehicle emissions impact air quality, visibility, and health. A recent study in the Proceedings of the National Academy of Sciences puts the number of excess deaths in the United States due to particulate emissions from transportation at 28,000 per year. Finally, transportation produces 29% of the U.S. greenhouse gas emissions, contributing to global climate change. A sustainable solution needs to address all of these things, but I'm going to focus primarily on greenhouse gas emissions. To address climate change, we need to dramatically reduce the CO2 emissions associated with transportation. But this is difficult because the transportation sector is driven almost entirely by petroleum. A good way to illustrate this is with a Sankey diagram. This diagram shows the flow of energy from sources on the left to consumption on the right. This Sankey diagram is for the US energy consumption from 2019. Looking down the left side of this figure, you see solar, nuclear, hydro, wind, and geothermal, all of which have nearly zero greenhouse gas emissions. But you see that essentially none of these flow into the transportation sector. In fact, transportation is powered almost entirely from petroleum, which has a high carbon intensity. Transportation uses about 70% of the petroleum consumed in the United States, and this is why transportation is responsible for about 30% of our greenhouse gas emissions. In fact, transportation is the largest source of CO2 emissions in the US. As of about February 2016, it surpassed electric power generation to take the dubious title of biggest climate problem. But notice that this isn't because transportation is getting a lot worse. It's because electrical energy generation is getting better. And this is good news. This is a picture of energy generation in the US. Coal, the black line, is on the decline. Displaced initially by the rise of plentiful, low-cost natural gas. That's the yellow and gold line. But what I want you to look at is the green line. The rapid growth of renewable energy generation is amazing. We see from this graph that non-hydro renewable energy generation has been growing exponentially for the past 2 decades. This graph shows newly installed generation capacity each year by fuel type. For the past decade, renewable energy generation has dominated the new energy generation installed, producing an increasing number of cheap, renewably generated electrons. This transformation of the electricity grid and the renewable electrons generated by this transformation create a huge opportunity to take greenhouse gas emissions out of the transportation sector. This slide is another way of looking at the information on the Sankey diagram. Today's transportation system is based almost entirely on a single energy source and a single energy carrier. Everything starts with petroleum at the top of the figure, plus biofuel that makes up a few percent of the feedstock. These combined make up the various versions of liquid hydrocarbon fuel that powers most of the transportation system. But this isn't sustainable. We're starting to see a growing number of light-duty electric vehicles on the road. In 2019, they made up about 2% of new vehicle sales, and that number is growing. But light-duty vehicles only represent 59% of the transportation greenhouse gas emissions. If we want to reduce greenhouse gas emissions by 80% or more, we need to target other transportation sectors as well. Some of the most crucial transportation sectors we need to address are medium and heavy-duty vehicles and aviation. Now I want to paint a picture of a possible low-carbon transportation future. I'm not predicting that this will be the future or even that this is the best future. I just want to create a vision for a possible low-carbon transportation future built on a backbone of sustainably generatable electrons to take advantage of the transformation we are seeing in the electricity sector. In this figure, we imagine an abundant source of renewable electrons. This is illustrated across the top of the figure where we show wind, solar, and hydro. This electron backbone could also include geothermal, nuclear, wave power, and tidal generation. There are many sources of renewable electrons, and different regions of the country will have different best sources. Along the bottom, we show the main transportation sectors. It's likely that almost all of the light-duty vehicle demand can be met with battery electric vehicles powered directly with these renewable electrons. We show these electrons routed through buildings and chargers to highlight the importance of infrastructure for distributing these electrons. And I'll talk more about that later. In the medium and heavy-duty vehicles, there are some vocations that are well suited for electrification as well, but most of the energy used in this sector is used by long-haul Class 8 semi-trucks. It isn't clear yet how much of this sector's demand can be met by battery electric vehicles. It may be that hydrogen fuel cell vehicles are needed. It may be that they continue to require liquid hydrocarbon fuels. As we move to the left, we get to marine and air travel. Although some fraction of these could be met with battery electric or fuel cell electric vehicles, it seems likely that a significant fraction of these sectors will continue to need liquid fuels. To meet this demand, we envision renewable electrons being used to produce hydrogen with virtually no greenhouse gas emissions. This hydrogen can be used directly as a transportation fuel for heavy vehicle applications. It can also be used as a low-carbon chemical feedstock for an electrons-to-molecules process in which CO2, either from the atmosphere or captured from other processes, is combined with renewable hydrogen and even more renewable electrons to produce liquid fuels. One thing you need to notice about this picture is that it's a lot more complicated than the previous one. There are a lot of interactions with the rest of the energy system. In this picture, we show the flow of energy and the many interactions associated with integrating all of these pieces into a full system of systems. On top of this, we could also add an information layer showing the interaction of these elements as part of the growing Internet of Things. We could also add a layer showing the effects of humans in the loop. The way people interact with technology and information will have a profound effect on how the system behaves and evolves. One of NREL's core competencies is system integration. We have the expertise and the facilities to attack these questions. This slide shows a schematic of NREL's recently announced Advanced Research on Integrated Energy Systems, or ARIES, research platform that is just coming online. This platform gives us the ability to explore system behaviors at multiple scales with diverse renewable energy sources integrated with increasing numbers of electric vehicles, smart energy management systems, distributed energy storage, and increasing electrification of building, heating, and cooling systems. Note that a key part of ARIES is the ability to combine hardware experiments with simulation results. Simulation is critical to understanding, optimizing, and controlling key elements of this system. These simulations range from the component level all the way up to the full system of systems. I want to walk you through a few examples of simulation work we're doing at NREL in the transportation field. At NREL, we do component-level simulations for batteries, power electronics, and electric motors, essentially any component relevant to vehicle electrification. This particular example is a simulation of an NMC battery electrode during a 20-minute fast charge event. Lithium-ion batteries are complex nonlinear systems, and it's imperative to understand the interplay between electrochemical, thermal, and mechanical physics. The streamlines in this picture represent lithium-ion currents in the electrolyte as the ions travel through the pores between the solid material particles. Models are places where we can bring all of the physics together and visualize what could be happening. In a simulation, everything can be measured, everything can be probed, and this helps us build an increasingly accurate physical understanding of the systems we model. In the case of this simulation, by simulating battery electrochemistry on various microstructure geometries, researchers can calculate the pore size of an electrode's microstructure geometry, as well as the lithium displacement within the electrode to evaluate the difficulty of movement. This helps us find ways to overcome resistances in the battery via microstructural modifications, and this can greatly improve overall battery performance. Now, shifting from the microscopic to the macroscopic, this is a project with the Dallas-Fort Worth International Airport that leverages data streams to model and optimize the integration of new technologies at DFW, as well as other transportation hubs. This project and projects like it utilize the DOE's high-performance computing resources and expertise to understand and optimize the integration of new technologies into the nation's transportation system. In this case, it's looking specifically at the interactions between the airport and the surrounding urban area. Airports are complex transportation hubs that coordinate the movement of passengers, goods, and services from the surrounding urban area. They need decision support and actionable insight to reduce uncertainty and mitigate risks for long-term planning. Another example of this sort of problem takes another step larger in scale. If we think about the problem of moving a city's worth of people in electrified vehicles, we have the twin problems of meeting the mobility demands and moving enough electrons to meet that demand with electric vehicles. If this is done with uncoordinated charging, grid stresses, especially from fast charging, could break the grid, resulting in overloading, poor power quality, and premature equipment wear. In this slide, we envision combining high-fidelity grid and transport models to identify effective pathways for widespread electrification, to design and evaluate integrated vehicle control schemes, and to increase resiliency of both the grid and the transportation system. This is not a simple problem. This slide is intentionally a spaghetti bowl, more to show the complexity of the problem than for you to really follow any of the arrows. In this workflow, you see a couple of things. First, we have scenario generating models for both transportation and the grid. These models take both internal and external inputs to generate scenarios that then further feed models of the infrastructure. These infrastructure models then feed a set of models which need to be co-simulated. This is the circle on the right side of the figure, showing a transportation network model, a vehicle charging model, and a grid distribution model being co-simulated. Helix is a flexible, scalable, open-source co-simulation framework designed to simulate regional and interconnection scale power systems. This example is from DOE's Smart Mobility Consortium. The DOE convened 5 of our leading national laboratories doing transportation research, including dozens of our nation's most talented transportation-related scientists and engineers, to build the Smart Mobility Laboratory Consortium, which is a multi-year, multi-laboratory collaborative of which NREL is a part. The goal of SMART is to understand the impact of connected, autonomous, and electrified vehicles on mobility, energy, and productivity. This modeling framework is a key part of that effort. At the center of the modeling framework are agent-based mesoscopic regional transportation models. The SMART Consortium has been using 2 of these models, the BEAM model out of Lawrence Berkeley and the Polaris model out of Oregon. Feeding into these models are electric vehicle charging infrastructure models, land use models, vehicle fleet models. Since we're looking at various levels of automation, we need to understand how these will impact traffic flow. This requires microsimulation with multi-vehicle collaborative controls to feed inputs to mesoscopic models that account for the changes in the way vehicles behave. From the regional transportation models, we can then assess energy consumption, congestion, travel time, and other metrics. These metrics are then fed into a comprehensive mobility energy productivity metric, which we creatively call MEP. MEP is a measure of accessibility weighted by energy, time, and cost. A higher value of MEP means you can access more goods, more services, and more jobs for less energy, less cost, and less time spent traveling. This example shows how a couple of different future scenarios might impact MEP in the Chicago area. Graphed here are changes in MEP from a baseline simulation. Green areas show increases in MEP, red areas show decreases in MEP. I won't go into the details of these three scenarios, but it's interesting to note that the different assumptions about levels of automation and trip sharing can have very different results, and those differences are distributed geographically in very interesting ways. Again, this is not a prediction of the future, but it demonstrates how we can use simulation to explore the intricacies of how all of the pieces of the puzzle may interact with each other in interesting and complicated ways. The last two examples used agent-based models to simulate human behavior. One concern that we have is that these agents may not adequately represent the complexity of human behavior. Within NREL, we have an active research project looking at the effects of including a larger number of more diverse agent populations, groups identified by key socio-geographic, socio-demographic, economic, and built environment characteristics. This potentially impacts how we think about transportation demand, building usage, adoption of new technology, and grid usage. The goal is to simulate people's heterogeneous behaviors, both in how they interact with technology and in how they adopt new technology. This is work in the early days, but we believe it could have a big impact on energy consumption and the distribution of energy consumption, both in time and space. All right, now this brings me back to ARIES. The energy systems that underlie our economy, our security, and our daily lives are changing like never before. To build a future energy system that is secure, resilient, reliable, affordable, and clean, we need research environments like ARIES that recreate real-world dynamics and provide space for exploration. The core of the ARIES platform consists of three elements at different scales. At the community scale are research assets and real hardware at the Energy Systems Integration Facility, or ESIF. ESIF is then connected via high-speed data link to city and campus-scale research assets at NREL's Flatirons campus. These interconnected pieces allow for experimentation at up to 20 megawatts and represents a research network at the leading edge of what's possible in the world today. A third, and a key innovation with ARIES that sets it apart from anything that currently exists, is the ability to amplify its scale through a virtual emulation environment. Powered by our high-performance computing resources, this virtual research space links our hardware experiments with our simulation capability. This will expand our ability to understand the interaction of hundreds to millions of devices within the complex energy infrastructures. To ensure that our future energy systems are sustainable, that our cities are livable places, that our transportation system is environmentally friendly, we must work together now to ensure we continue to advance this critical research. The existing transportation system faces a host of challenges which, left unaddressed, will have significant implications for our world. A truly sustainable transportation system will only exist when our mobility needs are met while preserving and enhancing human and ecosystem health, economic progress, and social justice now and in the future. Tackling these challenges will require informed decision-making supported largely by simulation and models designed and developed with sustainability considerations and objectives in mind. For those of you working in this field or aspiring to work in this field, your work is essential to ensure a cleaner, decarbonized transportation future. Thank you for your time.